Hey everyone, welcome back. So in this lecture, we're going to be doing something a little bit different, and I'm going to be sharing with you guys the walkthrough and the lecture directly in our studio. This, I think, might help some folks in terms of interpreting the RMD that they get. Again, when I'm making these PowerPoint presentations, it's just a knitted version of your RMD file. So it's the same content, it's just compiled a bit differently. But maybe we can get some feedback from you guys moving forward as we build this course, whether you prefer the lecture format to be in slides or directly in our studio. So let me know if you like this version better, but we're going to start here. Okay, so this is our regression lecture. We have a set of packages that we'll need to load. Again, some of these you'll already have. Palmer Penguins you'll have if you did the ggplot lecture with us. If not, you have to install the packages. Remember, that looks something like this. Install packages, and then it'll be in quotes, Palmer Penguins, something like that. But if you've already done this, you don't need to do this. But if you get an error code running this or like sjplot, it's probably because you haven't done the install packages. I have library Haven included because if I wanted to knit this, I'd have to have that and the path selected. Read SAV exists within Haven, and it tells the knitted file where to find my data set. So my data set lives here. You can get this line of code when you do this. When you import your data set from SPSS and you get this, the pop-up, when it runs it, it'll give you all of the information for that code, the reads SAV and your particular file path here. And it'll also show up down here in your console in the bottom left-hand corner. So if you want to have that information for yourself, that's where you can find it. So we've got all of our packages loaded that we need. We can then go ahead and start to look at the data set in Palmer Penguins that we're using. So for this lecture, we're going to be using the Palmer Penguins data set. And it exists within this package. So str is a function that gives us some of the details of the data set. And so we're going to run it. Again, you can double click and highlight it, line 26, and I can hit on Mac, it's command return, but whatever the command thing is on PC, you can hit command return. I can also hit this little green chunk and run it, and it'll give me all the same things. So it's a data set. A tibble is a certain kind of data set. It's in a tidyverse data set with 344 different observations or penguins and 8 different variables. The different variables are species, island, bill length, bill depth, flipper length, body mass, sex, and year. And you get a little glimpse of what those look like. So this is just a helpful package to know what you're going to be doing, what you're working with within the data set. And again, that data set in this case is called penguins, and it lives within this data set. So if you don't load this and you try to do this, it's not going to work. Okay, so we're going to have a hypothesis that we know can be tested within the regression setting. So we want a directional hypothesis, and we also want to be able to have full flexibility of the kinds of variables that we can use. Our outcome needs to be interval ratio, but we have a lot of flexibility in terms of the kinds of inputs that we can have are independent variables. So say we have a hypothesis that flipper length of the penguin systematically varies by species. Then some penguins, maybe such as like the Gentoo, are going to have larger flippers than others. So flipper length is our DV. And then our IV is going to be species. IV. So we could start by looking at the descriptive statistics of the relationship to kind of get a sense of what's happening before we run regression. So because we have an interval ratio variable, we can do a histogram. So we'll talk about this a little bit more in your last module for the quarter or the semester. But histograms are a great way to visualize this. So you're going to get all of this code, so no stressing about it. You're going to have a histogram made in ggplot that takes the penguins data set. In the aesthetic layer, we're going to say we want to use our x-axis, or that horizontal axis is going to be flipper length. And then we're going to categorize all of those different flipper lengths in the geom histogram argument to be by species. And then we want different colors for each of those species. And then we have some labels that tell R what we want those axes and things to be called. So we're going to run flipper histogram. Okay, so we know it worked because in my environment, I have this new object here on the top right-hand corner called flipper histogram. So I know that it ran because it's here now. And then there's a couple different ways that I can get at that histogram. So if I were just to run this without creating the object, which is that arrow, if I ran it like this, it would come out here at the bottom. So that's one way to get at the histogram. But also I stored it in this object, right? So now, actually, in this case, we can just double click and run line 54, either with command return, or I can just run the chunk with the little green arrow and I'd get that. So what we're getting at here is that flipper length on the x-axis. So it goes from like 150 to 250, let's say, millimeters, the flipper length x-axis. And then the y-axis is the amount of penguins that are in each of these different flipper lengths. We see that Adelaide's, it looks like these orange ones have some of those smaller flipper lengths. Chin straps are sort of in the middle. And then Gen 2 seem to have the longest flipper length. So we have some kind of tentative evidence of our hypothesis that flipper length varies by species, and that Gen 2 are going to have the largest. But we don't, in this case, have any sort of inferential understanding of whether this is a statistically significant result. So again, this is taking the ggplot code here, and then we're opening and running the object here in a few different ways. You can either, again, use the little green arrow or command return on this line. You can either highlight it, or you actually can also just put the line on the cursor and hit command return. So a lot of different ways to run the code. So we know that we need something like regression. In this case, we've got an interval ratio variable. We want to know the actual magnitude difference in the impact on flipper length by species, and we want to know the direction. So we get a lot of information from regression. So we're going to run this first line of code, which is a single variable regression. Now, RStudio and R is going to run regression in the same way with the tilde language that we used earlier with t-tests, where our dependent variable is on the left and our independent variable is on the right. We also are going to specify what our data is called, and our data is called penguins. Now, you'll notice that you don't have to use $signs here. Why? So this function, the linear regression function, instead of reading like we do from left to right, it reads from right to left. So when it goes from, it starts here and goes this way. So the first thing it reads is the data set that we're selecting from. And then from that data set, it selects species and flipper length. It regresses species on flipper length. So in this particular case, we don't need the $sign because in the direction that R is reading it. Okay, so now we have this new object called regression 1. It's stored here. We see it, right? We know we ran it. So we're going to run it one more time, and then we are going to put that regression object into summary. So when we just run regression on its own, right? So I can double click and highlight regression _1 and just run that without putting that function or that object into anything else. And we see that there's a little bit of information. We don't have anything about a test statistic. We don't have anything about a p-value, degrees of freedom, any of that. So we do calculate that with the LM function, but in order to see it, we have to use a very specific next function called the summary function, which takes all of that information from our regression object and puts it into a table that helps us. This is really what you want to be interpreting. This comes from line 66. Which is the summary regression _1 function. So the summary function is taking our regression object from line 64. Cool. So we have all of the information that we have talked about a little bit in terms of your guest lectures for regression here. So there are two different species, right? And each of these are interpreted relative to the reference level or the group that's omitted. So we'll start with the Gen 2 species because that was our main hypothesis, that their flipper length was going to be bigger. And we do see that Gen 2, as compared to Adelaide, which was the next closest group and the one that was omitted because we only see 2 here, right? We got Gen 2, chinstrap, Adelaide are our 3 species. The Gen 2, as a penguin is Gen 2 as compared to an Adelaide, their flipper length increases by 27.233 millimeters. And so as we have a Gen 2 penguin as compared to an Adelaide penguin in this case, because that was the group that we're comparing against, right? We know we're comparing against Adelaide because they're not shown in the output. The flipper length increases by 27.23. And this makes a lot of sense, right? Adelaides are smallest. And so we see that Gen 2s compared to Adelaides are going to be a lot bigger. And on average, it's going to be by about 27.233 millimeters. So this makes a lot of sense. We also see that on average, the chin straps are about 5.869 millimeters larger than Adelaide's in terms of their flipper length. And that makes sense too, right? Think about where the mean or the central point is for Adelaide versus chin strap, right? That central point for chin strap is definitely a lot higher than for Adelaide's, right? So the central part is where most of the data is, most of the frequency is, right? The tallest point for this is higher than the tallest point for this in terms of our x-axis, right? The tallest point here is probably like 184, and the tallest point here is probably like 195. And so we know that they're a little bit bigger. And these all are statistically significant because we have p-values less than 0.05. We know that both because of the number and because of the significance code. So these are really helpful. Okay, so if the p-value is just about 0, there's going to be 3 stars. If the p-value is around 0.01 or less than 0.01, it's going to be 2 stars. And if it's less than 0.01, it's going to be 1 star. And so in this case, we're actually able to use these stars to kind of have a good guide on whether or not we reject or accept our null hypothesis. And in this case, because we have 3 stars and we're less than 0.05, we can reject the null hypothesis that species does not vary by, flipper length does not vary by species, and Gen 2 are in fact bigger in terms of flipper length than their companion species. Again, we also get the intercept. The intercept is our baseline value of the y-axis, or just our average value of flipper length when we don't take species into account. So if we're not looking at species whatsoever, we would think that the average flipper length is at about 189.95, which is like, we'll say they're like probably right here, which makes sense. We had 2 species overlapping with each other, but we know that we're missing a lot there, right? In terms of both how far this is off based on the rest of the different species, and based on, you know, our interpretation of our significance and our ability to reject the null. So we get a lot of information here. We also know that we get R squared here. So there's multiple R squared and adjusted R squared. In terms of interpretation, I want to use the adjusted R squared. It just has a sort of penalty for the amount of independent variables you use. So it adjusts for adding a bunch. So that's beyond the scope of this course. But when you see these, I want you guys to be interpreting the adjusted R squared. And the adjusted R squared in this case is 0.7769, which means 77% of the total variation of flipper length is explained by species. So we are doing tons of the explanation of our dependent variable flipper length by including the species independent variable, right? Adjusted R squared, or R squared, is from 0 to 1, and 0.77 is the vast majority of it. Most of the time in social science work and our political science data sets, we're somewhere like, we're doing a good job if we have like 0.3, right? 30% of the total variation explained. It changes a bit when you're in these sort of hard sciences and doing things like STEM work or this sort of biological work. Usually those numbers for the R squared are a lot higher. But in this case, with our kind of more STEM biological example of these penguins, we get a lot of information explained by species and chin strap. And this also really comports with our understanding from the histogram too. The histogram is really powerful in terms of showing us that the flipper length really does vary by these species. We just need to be statistically sure of that by doing regression. All right. So we know that we can have single variable regression or multivariate regression. So multivariate regression is when we have more than one independent variable. So in this case, we know that species matters a lot, but we also have the independent variable of island. Maybe we think that certain penguins on certain islands are getting fed a little bit more, so they're bigger on certain islands. That could be a like fictional hypothesis for that. So we'd want to include that. In order to add additional independent variables of interest, we add a plus sign, and then we add that new variable. Again, we don't need the dollar sign because we've already specified it, but we're going to have our dependent variable with the tilde sign, and then independent variable plus independent variable, and then comma our data set. So we'll run it. We know that it exists because we have regression 2 over here on the right-hand side, and we know we need to put it in the summary function. Now, we still see the interesting, kind of significant finding of species, but we also are now able to see that because we included island, we see that there's no statistical difference between flipper length and different penguins on different islands. We know that both because of the size of our p-value, which is much, much larger than 0.05. We also are missing stars, right? So 0.01 is the period. And so we see that we're actually not able to get towards statistical significance. And so actually this is 0.05, but it's greater than that. So this is on the outside of that threshold. And so we know that we did a multivariate regression. We also tested to see if the flipper size varied by the different islands that the penguins were found on. And it doesn't particularly matter what island it was, it just mattered what species. So we have these different regressions. We want to kind of include them in our final research paper or our findings. And so what we're going to do is we're going to use the SJplot package, and we're going to run this function called tab model. When we run tab model and put our regression in tab model, we're going to get something over here on the right-hand side. And that is actually just going to give us exactly what we had here, but instead of screenshotting this kind of mess, it gives us a pretty HTML version of the table that we can screenshot and put in our final papers. And so it has all the information you need, the coefficient estimate or a beta estimate, the confidence interval. We can be 95% confident that the estimate for chin straps is between 3.96 and 7.78. Same thing for Gen 2. With our p-values, it rounds your p-value and then gives you an r-squared adjusted, right? So 0.777, and then also gives us an n, or the amount of observations we have. We can do the same thing for our second one. Let's go ahead and just put that here. And we can see that it does the same thing, right? It just adds our additional variables, right? Because we specified the second multivariate regression. And that got us to a place where we were able to see that there was not a significant difference between the different islands penguins came from. Okay, so we have all of this information, but we also at some point are going to want to show you how to plot this information, right? So we saw in correlation work that we were able to plot it on a scatter plot. We also, right, this was the line that went through the scatter plot. We also were able to, I'll show you in future lectures that we're going to be able to plot this. So I'll give you a little bit of a teaser of what that looks like now. So also in the SJplot package, there's this awesome thing called plot model. And so in this case, we can use the plot model function and then do, let's just say regression 2, and it'll give us a dot and whisker plot. A dot and whisker plot gives us the point estimate, or this kind of on the right-hand side, our coefficient beta estimate and the confidence interval on a number line. And so in this case, we're able to see, so like the species chin strap, that estimate over here on the right-hand side is 6.09. Well, you can see that this very top row, species chin strap, the dot sits on 6.09, and then there's a confidence interval that ranges from 3.74, which is the left-hand side of the whisker, to 8.84, which is the right-hand side of the whisker. And so you'll see moving forward that we can do this to visualize our regression estimates for your final paper. I also just highly recommend maybe looking at regression as the option that you use for your final paper. It's really flexible based on the kinds of variables that you want to be using. And so I think this is a good option for you guys to pursue for your final paper. But in the final paper, you have obviously full autonomy to pick any of the inferential statistics options. And I'm going to show you in your next set of lectures in the extra credit portion of this course, how to plot those for the final paper, regardless of what you choose.